Unit 2 review over limits. So I'm going to go through all these questions, and hopefully have a chance to go over it that you're still confused on with me in class before we take our test on limits. All right, so let's get started. Number one is looking at this exponential function here, talking about the population of bacteria. And it says, which of the following gives the best estimate for the instantaneous rate of change of P at time equals 8? So that's like right there. All right. And it essentially what this is doing is, you'll see when we get into our next unit on derivatives, is that it's getting you started to thinking about looking at the slope of a line that is tangent to a curve at some point. So this line that they drew is tangent to that exponential curve at the point t equals 8. All right, all that being said, we want to find the slope by looking at values that are really close to t equals 8. So when you're looking at these answer choices, you're looking at B, C, and D essentially. And the one that has the points really, really, really close to t equals 8 is going to be letter D. Number two is looking at the best estimate for the speed of the particle at time t equals 6. So right here is the position, and very similar to kind of the last one, we're trying to figure out the slope of the line that's tangent to this curve. But if you'll notice, this curve is actually a line. So if we're trying to find the slope to get the instantaneous velocity or speed of this particle at time t equals 6, we can just find the slope of this line. So finding the slope of this line, I can use these endpoints of this piece of that line, and that's going to be the points 0, 10, and 8, 20. So if I find the slope, I'm going to do my change in my y over the change in my x, and that gives me 10/8. All right, you'll see the answer choices, none of these answer choices are 10/8, but if you reduce that, you get 5/4. Number 3. All right, this one says, what is the limit as x approaches 2 of this function? Now, as we've been talking about for a long time with limits, as long as you approach this 2 from the left and from the right and you get the same y value, then you know that the limit exists. So even though there is like f of 2 is actually positive 1 because it has removable discontinuity there is a hole. The limit as x approaches 2, right, as I'm approaching from the left and the right, is actually approaching that y value of 4. So the answer is 4, even though f of 2 is a different value. Okay, that's something we talked about many times before. So 3 is C. Very similar to some problems we did at the very beginning of this unit. All right, looking at tables of values. When you are looking at x approaching 7, you want to be approaching 7 from the left and from the right, so like 6.99999, 7.00001. So that kind of eliminates A. All right, and then we should be approaching 6 from the left and from the right. So like letter D is wrong because the one that's approaching it from the left is actually not approaching 6. This one looks like it could be right, but they're really, the one on the right is really approaching 7. So the only one that's approaching 6 from the left and the right is answer choice B. Okay, number 5. All right, which is the following is the best interpretation? The limit as x approaches 3 of f of x equals 5. So it says in part A, or in answer choice A, the value of the function f at x equals 3 is 5. That could be true, but as we talked about a few problems ago, that doesn't have to be true because you can still have a limit exist even if your y value is a different value, right? That's called removable discontinuity. This one is kind of just going backwards of part A. So it really comes down to C and D. And as you know, we read this as the limit as x approaches 3, the value of f of x approaches 5. All right, so 5 is C. All right, number 6. Which of these statements are true? All right, the first one says the limit as x approaches 2 from the left. Hopefully you can see that there. That's a negative sign. So 2 from the left, let me change colors here. So 2 from the left is going to be like this, and it approaches negative 1. All All right, and f of 2, because it's a closed circle, is -1, so that checks out. X approaches 6 from the left, right, and 6 from the right. All right, those are actually the same. They're approaching -1, so that's true too. And then the limit as x approaches 6 is actually -1, but f of 6 is actually -3. So this would be -1 equals -3, which is not true. So only 1 and 2 are going to be true. So looks like that's C. Number 7. It says, which of the following statements is false? Okay, well, let's see. The limit as x approaches 2 exists. Let's see. So as I approach 2 from the left and from the right, we approach a y value of 2. So that does exist. So that's not false. The limit as x approaches 3 exists. As I approach it from the left and the right, yep, we're approaching that y value of 5. So that also exists. The limit as x approaches 4 exists. Well, when I approach 4 from the left, I approach this y value of 2. When I approach it from the right, I approach a y value of 4. This limit does not exist because as you approach it from the left and from the right, they don't link up. They don't hit the same value from the left and from the right. So the limit as x approaches 4 does not exist. So 7 is going to be C. Okay, number 8. For what values of A does the limit as x approach A of f of x equal 0? Okay, well, let's look at 2. So let's see. From the left and from the right, we're approaching 0, so that works. All right, let's check. Or I should say, let me not check that. Let me just write 2 works so far. Let's try 4. All right, 4 works from the left and from the right. That one also works. Let's try 0. From the left and from the right of 0, they don't actually approach the same y value, so 0 is not going to work. So it's just going to be 2 and 4, or B. Okay, number 9. What is the limit as x approaches 1? Well, as you approach 1 from the left, you approach the y value of 3. When you approach 1 from the right, you get the y value of 1. Those don't match, so this limit is not going to exist. So that's going to be D. Number 10. We have a piecewise function. It says the value of the limit as x approaches 2 from the right. So when I'm looking at my piece value function, I have these x values here for less than 2, equal to 2, and greater than 2. When you're approaching from the right, you're approaching from x values that are greater than 2. So I'm going to focus on using this piece and plugging in 2, which is going to give me 11. So 10 is C. Okay, now if I were to plug in -3 to try to evaluate this limit, you're going to see that I get 0 over, let's see, this is going to be 9 plus 6 is 15 minus 15 is also 0. But you should notice that these are both quadratics, so I'm trying to factor them to get, this is the difference of 2 squares. And in the denominator, I have factors of -15 that add to -2, so that's going to be -5 plus 3, so you'll see my common factor. So the limit as x approaches -3 of x minus 3 over x minus 5. Now I'm going to plug in -3 after I've crossed out my common factor to get -6 over -8. So reduce, that's going to be positive 3/4. Number 12. Now for this one, I'm going to type this into Desmos because I see the absolute value symbol, and that tells me that something interesting is going to be happening. And I'm looking for the limit as x approaches 3 from the left of this function. So x, the absolute value of x minus 3 over x minus 3. So I have the absolute value, again, there we go, x minus 3 over x minus 3. And I'm approaching 3 from the left. So 3 from the left is going to be approaching a y value of -1. So that's going to be B. Okay, 13. Now I guess I should say before I move on, if I was approaching 3 from the right, that'd be approaching a y value of +1. And if it said, what's the limit of this function as x approaches 3, because those don't link up, it would be does not exist. Okay, 13. Now 13 is interesting because it's asking us to find the limit as x approaches pi over 4. And if I were to plug in, let me do this, pi over 4 here, so cosine of pi over 4 squared over the cosine of pi over 4 minus the sine of pi over 4. Let's do a little work here. If you need me to open up that trig formula sheet, I can. All right, for the cosine and the sine of pi over 4 here at the bottom. All right, we have the sine and cosine of pi over 4 is actually the same, square root of 2 over 2. So that's going to be the square root of 2 over 2, but that's going to be squared. So that's going to be 2 over 4. And if you multiply by it, that's a half times 2, which is 1 minus 1, or 0. And then this is going to be the square root of 2 minus the square root of 2, which is going to be 0 over 0. So I can't deal with that, right? That's a problem. But if I were to look at the numerator, you'll see the numerator says 2 cosine squared x minus 1. And if you look at right here, the double angle identities, all right, that's the same as the cosine of 2a. And actually what I'm going to do is I'm going to first copy this down and multiply by the conjugate of the denominator, cosine of x plus the sine of x. I think you'll see what happens here. So I'm going to keep the numerator the same, just leave that alone for now. All right, so don't actually distribute the numerator. But in the denominator, right, this is going to become cosine squared x minus sine squared x. All right, here's where it gets interesting. If you look in my double angle identities, the cosine of 2a can be equal to one of 3 different identities. It can be equal to cosine squared a minus sine squared a, or the second one, 2 cosine squared a minus 1. If you look at that, I have both of those in my function right now. I have one on the top and one on the bottom. So essentially, I know it's kind of interesting, or you might have forgotten from your days in trigonometry, but this right here and this right here are actually the same. They're both the cosine of 2x. All right, so I can actually cross those out because they're the same, and I'm left with the limit as x approaches pi over 4 of cosine of x plus the sine of x. So that's going to be equal to letter B. Key takeaway from this is not necessarily like you need to stress about the trig, although you will have the formula sheet if you need it. The key thing is to focus on that idea that you can always multiply the conjugate, and that might help you kind of figure out what to do with your limit. All right, another example of using the conjugate, right? If I plug in 1 here, I get 1 minus 1 is 0. Square root of 1 is 1, minus 1 is also 0, so I can't evaluate this right now. But I can factor the numerator and then multiply by the conjugate, the square root of x plus 1. Leave the numerator alone for now. And my denominator becomes x minus 1. Right, you'll notice I can have a common factor to cross out. So now I have the limit as x approaches 1 of x plus 1 times the square root of x plus 1. Now you can plug in your number and you get 2 times square root of 1 is 1 plus 1 is also 2, and you get 4, which is A. Okay, 15. All right, now this one is the AP test way of talking about the squeeze theorem, which we talked about if you have 2 functions that are kind of the bread of your sandwich, in between the function you care about, the meat of it, if you find the limit as x approaches a number is equal to the same value for the pieces of bread, then in between that meat, the limit as x approaches that number of that function will also be the same. So all of this is just essentially saying if I plug in -1 into my g of x function and my h of x function, and they're the same, then the limit of as x approaches -1 of f of x should also be that same thing. So let's plug it into the g of x function. So sine of pi over 2 times -1 plus 2, and then all that plus 3. Let's see what we get. Well, -1 plus 2 is 1. So 1 times pi over 2 is still the pi over 2. So the sine of pi over 2 plus 3. All right, I know what the sine of pi over 2 is. If you need to look at your quadrantals, all right, you can. So the sine is going to be the number, that y value of +1. So 1 plus 3 gives you 4. Let's plug in -1 into the h of x function. So -1/4 times -1 cubed minus 3/2 times -1 squared minus 9/4 times -1 plus 3. So that's going to be a negative times a negative is a +1/4. That's going to be a positive times a negative, so that's a -3/2 plus 9/4 plus 3. All right, so 1/4 minus 3/2 is going to be -5/4. -5/4 plus 9/4 is 4/4, which is the same as 1. 1 plus 3 is 4. So because they're the same, I know that the limit as x approaches -1 of the function that's being squeezed by these two is going to also be the same thing, which is 4. Okay, 16. It tells us that the function is increasing for values of x that are less than 1 and increasing for values of x that are greater than 1. And the limit as x approaches, if the limit as x approaches 1 is 5, which of the following could represent the function g? Well, when I look at the first one, it's piecewise, right? So when you approach 1, right, the first instinct to look at for the piecewise function is, okay, well, when you use 1, you get 3. But as I've mentioned multiple times in this review already, just because g of 1 is not equal to 5 doesn't mean your limit could not equal 5. So as we're looking at values from the left and from the right, if I evaluate x squared plus 3x minus 4 over x minus 1 at +1 and get 5, then this could actually be the answer, or one of the answers. So let's factor. So x plus 4 and x minus 1. The x minus 1s are going to cross out. So that leaves you with just x plus 4. If you plug in 1, you get 5. So that actually does work. Looking at the table in number 2, as I approach 1 from the left and right, even though g of 1 is 5, it looks like I'm approaching infinity and negative infinity from the left and from the right. So that's not going to work. And in number 3, as I approach it from the left and from the right, I'm approaching that y value of 5. So 3 would also work. So 1 and 3 are going to work, which is D. Okay, 17. 17 says, at what value of x does f have jump discontinuity? And so just as the name sounds, you essentially have to jump from one piece of the function to the next. So if I'm looking here, this has removable, right? This is removable here. But this one is literally jumping, right? All the way down there. So x equals 7 is going to have jump discontinuity. Remember, there's 3 different types. There's removable, which is holes, jump, which we just described, and then infinite discontinuity, which is when you're going to see those vertical asymptotes show up. Okay, 18. Which of the following statements is true? So for this one, what I notice is I can factor out an x in the top. So I'm going to factor out an x and get 3x squared plus 2x over, and factor out an x in the bottom, x times x minus 1. So this is actually a hole at x equals 0 and a vertical asymptote at x equals 1. So understanding that stuff that you did in Algebra 2 and pre-calculus is going to help you kind of make the transition into some calculus here with some limits. So we have 2 different types of discontinuity. Remember, the hole is the removable one, and the vertical asymptote is called infinite discontinuity. So when I look here, I have a removable discontinuity at x equals 0 and a discontinuity due to a vertical asymptote at x equals 1. So this one's going to be C. Okay, 19. What are values of x for which this function has removable discontinuity? So again, that's going to be the time you have holes. This is that jump discontinuity at x equals 5, so that doesn't work. but you have removable at 1 and 7. So that's going to be C. Okay, which of the following functions are continuous at x equals 1? All right, so you can go to Desmos and look here, but when I do the natural log of 1, I get 0. E to the first power equals E, and then e to the first power is e. E minus 1 is going to be a natural log of a number that's over 1, so this is a positive number. So we should be good. Let's go to Desmos, and I'll type them in, and you can confirm visually that these are going to be continuous at x equals 1. So we'll start with the natural log of x. Right, so there's x equals 1. It's actually, as we noticed, our x-intercept. So continuous from the left and from the right, no problems there. Then we have e to the power of x. Again, 1 is going to be 1 comma e, which is approximately 2.718, so no problems there. The last one was, I think, the natural log of e to the x power minus 1. I'll confirm. Yes. And for this one, your 1 is going to be, I got positive number 0.541 approximately. Okay, so again, all three of these are fine. They're all continuous, so the answer is going to be E. Almost there, 21. It says, if the function is continuous at x equals 3, what is the value of k? Now, with piecewise functions, guys, if these are going to be continuous, which means we don't have any jump discontinuity, we need to make sure that as we approach 3 from the left and from the right, they actually end up having the same value. So x squared plus 2 has to be equal to 6x plus k when x equals 3. All right, so I'm going to plug in 3 for x, and then solve for k. That's going to be 11 equals 18 plus k, so k equals negative 7. So A. Okay, 22. If the limit as x approaches b exists and f is not continuous at b, then b it could possibly be. All right, so let's go negative 1. Well, the limit as x approaches negative 1 does not exist, because you'll notice that we're approaching negative infinity and positive infinity from the left and from the right. So that's not even going to be existing also. So that's why A is wrong. As approaching 0, the limit does exist, but f is continuous, so there's no issues there. I lied. I'm sorry. That's the answer, because we have removable discontinuity, so it's not continuous. That's my fault. There is a hole there. All right, so that's going to be fine. Let's look at 1. The limit exists and is continuous, so that's why that one's not right. That was my brain thought it was going to be. It's my fault. And then for 2, it's not continuous because we have jump discontinuity, and actually the limit as x approaches 2 does not exist because they don't have the same y values from the left and from the right. So 22 is B. 23. Okay. A student was attempting to confirm that this function is defined, that this function is continuous at x equals 2. In which step, if any, does an error first appear? Well, the first thing they did was they factored. That's a good idea with quadratic trinomials. Then they crossed out their common factor, right, this x minus 2's, and found the limit exists at negative 5/3. But here's the problem. When you do f of 2, you actually have to plug 2 into the original. So they should have done 2 squared plus 2 minus 6 over 2 squared minus 7 times 2 plus 10, which is going to give you 0 over, let's see what happens here, 4 minus 14. Yeah, it's going to be 0 over 0. So it looks like step 3 is the problem. All right, and it's not continuous because you have a hole, so we have removable discontinuity at x equals 2. So even though the limit does exist, it's not continuous. Okay, 24. Which of the following is true? F is discontinuous at x equals 0 because the limit as x approaches 0 of f of x does not exist. Well, it is discontinuous, but that's actually not why it's discontinuous, because the limit actually does exist, right, as you approach it from the left and from the right. Let me change colors here. When you approach from the left and from the right, you're actually approaching the same y value. All right, it doesn't exist because it has removable discontinuity. Let's look at x equals 3. It is discontinuous. That actually looks like it could be the answer because f of 3 is not the same as the limit as x approaches 3 because of that removable discontinuity. F is discontinuous at x equals 5. Actually, the limit as x approaches 5 from the left does exist. It's this y value of 4, so that's not it. And then at 6, it's actually continuous at 6 because the limit as x approaches 6 and f of 6 are the same. So that's not going to be the answer. So the answer is B. Okay. We're trying to figure out another one where a piecewise function is continuous at x equals 3, so they must be the same. So a squared plus x squared must be equal to a times x plus 3. So I'm going to plug in 3 for x and get a squared plus 9 equals 6a. I'm going to move that 6a over with subtraction to set it equal to 0 and factor. And you actually get a minus 3 squared. So the value for a that's going to make this true is positive 3, or B. All right, just a few more left, then we'll be done. Number 26, all right? This is saying the limit as x approaches 1 from the left of f of x is positive infinity, and the limit as x approaches 1 from the right, is positive infinity. This is, or negative infinity. This is telling me we're going to have a vertical asymptote at x equals positive 1. And then all of the stuff that it's saying about the limit as x approaches negative infinity is 2, as the same thing as x approaches positive infinity, means we have a horizontal asymptote at y equals 2. So I'm looking for, all of these have that except for, let's see, this is switched. This one is got a negative 2, so I don't want that. So it's really A or C. And as we approach it from the left, let's make sure here, as we're approaching 1 from the left, it's approaching positive infinity, but this is approaching negative infinity. So this one's approaching positive infinity. This one is negative, and then we have our horizontal asymptote right there. So C is going to be the answer for 26. Okay, 27. We're trying to figure out the values for A and B to make this true. And the first thing I notice is we have a vertical asymptote at x equals 2. So when I see x squared plus b, all right, I need to figure out what makes this 0. All right, and it makes it 0 at positive 2. All right, so my thought is if this is x squared minus 4, then I factor, and you have a vertical asymptote at x equals 2 and negative 2. So my first thought is b is going to be negative 4. That's my first thought, which that actually would give me the answer. But let's talk about my a value. All right, if you remember from your days in pre-calculus in Algebra 2, to find the horizontal asymptote when the, let me zoom in on it, when the degrees are the same, if you remember that right there, when the degrees are the same, it's y equals the leading coefficient of the top over the bottom. So that would be a over 1 must be equal to 3. So a has got to be positive 3, which matches what I was thinking with answer choice D. All right, last two. It says we have a continuous function that's positive and has domain x is greater than 0. All right, so we'll draw my little sketch. I have asymptotes are, let me get my asymptotes on here with pink. X equals 0 is the y-axis, and y equals 2 is right here. We're saying that the function is positive. All right, the function is positive. It has domain x is greater than 0. So actually that means I have to have a curve that looks like this. So I'm trying to link up these answer choices with what's happening in this curve. So x approaches 0 from the right. That looks good. This piece looks good. But x approaches 2 is not going to be what I'm looking for here, so that's wrong. So that one's not going to be right. Okay, this looks like it could be good. That piece is the same. And then as x approaches infinity, we have a y value of 2. So C is going to be the answer for 28. All right, finally 29. Kind of similar to the things we've done the last few questions. The vertical asymptote means that your denominator equals 0, and we need that to be x equals negative 3. So if you think opposite, that's going to be x plus 3 equals 0. So C is going to be positive 3. And then for the horizontal asymptote, you'll notice again that the degrees up here are the same. So A has to be that horizontal asymptote of 2. So these are A and C. And then it says, what is A plus C? Well, A plus C is going to be positive 5. All right, guys, that's it for the review. Hopefully you'll feel very confident after watching this to take the test on limits. Good luck.